Hello everyone. Thank you for attending this session. I'm Yoshiyuki Tabata from Hitachi Ospo. Today, I'd like to talk about securing AI agent infrastructure, authentication and authorization patterns for MCP and A2A. In this session, I'll share practical authentication and authorization patterns to secure AI agent infrastructure with a focus on MCP and A2A. We'll grant the discussion in the CNCF IAM white paper, which is expected to be published in the near future, and then map these principles to real-world implementations using Keycloak and Spire. By the end of this session, you will have a practical blueprint for moving from concept to implementation. So this is today's agenda. First, I'll explain what MCP and A2A are and why they emerged. Next, I'll introduce the CNCF IAM white paper principles and discuss why they matter for agents. Then I'll present concrete authentication and authorization patterns for MCP and A2A. Finally, I'll provide a demo showing these ideas in action using Keycloak and Spire. First of all, let me introduce myself. My name is Yoshiyuki Tabata, and I'm a senior OSS consultant at Hitachi. I specialize in securing API and identity for enterprise and cloud-native platforms with over 10 years of experience designing secure API ecosystems and identity solutions. As a tech lead for CNCF tag security and compliance, I contribute to best practices, white papers, and proposal reviews and facilitate meetings in the APAC region. I'm also an active open source contributor, especially to Keycloak as a language maintainer and a feature developer. And in addition, I organize community events such as Keycloak Japan, speak at conferences like KubeCon, and write books and articles on IAM and Keycloak. So let's get started. We'll start with what MCP and A2A are. Before AI agent, LLMs could only suggest steps, and users had to manually execute each action themselves. This limited both speed and consistency. AI agents changed this by acting on the user's behalf, automating tasks under human supervision. As the responsibilities of AI agents increased, they needed to communicate with a wide variety of protocols such as SQL, CLIs, REST APIs, and many others. This diversity made integration complicated and often inconsistent. To address this, MCP and A2A were introduced to bring standardization. By adapting these standard protocols, we can reduce the need for custom adapters and make interoperability much easier and more reliable. So first, what is MCP? MCP is a protocol that standardizes how agents discover resources and exchange context with external tools and services. A key authorization feature of MCP is that it requires agents to use the OAuth 2.1 authorization code flow to obtain an access token for accessing MCP servers. I'll explain the MCP authorization flow in detail. First, when an agent wants to access an MCP server, it first sends an MCP request without a token. The server returns a 401 unauthorized and www authenticate header, indicating that authentication is required. Then the agent retrieves the protected resource metadata, including its authorization server information. Next, it obtains the authorization server metadata to get to know how to communicate with the authorization server. And then, if necessary, the agent performs dynamic client registration. After that, the agent uses the OAuth 2.0 authorization code flow to obtain an access token from the authorization server. Finally, the agent makes an MCP request to the MCP server, this time including the access token. By following this standardized flow, MCP enables consistent and secure delegated authorization for tools and services. Next, what is A2A? A2A focuses on agent-to-agent communication. it also defines how agents discover each other. As you can see, the A2A authorization flow is much simpler than the MCP authorization flow, and the interaction of obtaining credentials is out of scope. And the A2A allows us to use not only an auth token, but also API keys and other supported methods as credential to access A2A servers. Then, how do MCP and A2A work together? As shown in this diagram, which is referenced from the A2A website, MCP and A2A often coexist in real-world systems. MCP is typically used for agent-to-tool communications, while A2A is used for agent-to-agent communications. However, if A2A uses weaker credentials, such as API keys, it can become the weakest link in the security chain. To maintain a consistent and strong security posture, it's important to align A2A with the same level of assurance as OAuth 2.1, just like MCP. So next, we introduce the CNCF IAM white paper and link it to MCP and A2A. This slide gives an overview of the white paper. The white paper, which is expected to be published in the near future under the CNCF Identity Access Management Initiative, defines key requirements for authentication and authorization in cloud-native environments. It introduces two security patterns, basic and advanced, to address different security needs. For each security pattern, the white paper defines both authentication requirements and authorization requirements. Authentication requirements are further divided into user authentication requirements and workload authentication requirements. These requirements are based on several standards as best practices, such as OAuth 2.0, OpenID Connect, the ZACML P2P architecture model, SPIFFE, and NIST SP 800-63 digital identity guidelines. So why apply IAM principles to MCP and A2A? Agents communicate over HTTP APIs, so they inherit classic API security risks. And the OWASP API security top 10 remains highly relevant here. 4 out of the top 5 risks are related to broken authentication and authorization, making them the most critical security issues for APIs. In addition, the OWASP top 10 for LLM applications also repeatedly points out the importance of authentication and authorization. All of this shows that robust authentication and authorization are essential for securing agent interactions. This is why applying IAM white paper principles helps mitigate these risks and ensures secure and reliable agent communications. And the white paper defines 2 target use cases, stateful workload use case and stateless workload use case. I will omit the detail, but MCP and A2A endpoints are generally treated as stateless from an authentication and authorization perspective. This is because each API request is independently authenticated and authorized. This is regarding the security pattern. As I mentioned in the overview, there are 2 security patterns, basic and advanced. I'll explain these security patterns in more detail here. The basic pattern is recommended for systems with limited external exposure and non-sensitive data. It mainly addressed external threats such as unauthorized access and impersonation at the perimeter. On the other hand, the advanced pattern is necessary for systems that handle sensitive data, connect to public networks, or are used by an unspecified number of users. It addresses internal threats such as lateral movement and compromised workloads. In the best pattern, the entire cluster is treated as an implicit trust zone, and API clients obtain an access token and send requests to the perimeter workload. This perimeter workload validates tokens and delegates authorization to policy decision point over PDP. For internal communication between workloads, token exchange, and adding access tokens are optional. In the advanced pattern, each workload is treated as its own implicit trust zone. All service-to-service traffic within the cluster is secured using SPIFFE-based mutual TLS, so every connection is authenticated and encrypted. External access tokens are exchanged for internal access token before being passed to downstream workload. At every workload, authorization is enforced by evaluating policies via the PDP. This approach defends against lateral movement and credential replay, providing a zero-trust environment inside the cluster. From now on, I introduce the 5 key IAM principles, but today I will not go into the details of each principle due to the time constraints. So for details for each principle, please refer to the white paper. The first principle is SPIFFE mutual TLS. That is a mechanism that encrypts communication and authenticates both parties using mutual TLS. The second principle is OAuth 2.0 token exchange. It is a process that replaces external access tokens with internal access tokens for downstream calls. The third principle is OIDC client authentication with SPIFFE SBIT. It uses SPIFFE verifiable identity documents to authenticate workloads to the OIDC OP. The fourth principle is OAuth 2.0 access token validation. This verifies the signature, issuer, audience, expiration, and revocation status of access tokens. The final principle is PDP-based authorization decision. It delegates authorization evaluation to a PDP, separating authorization logic from application logic. Okay, so now let's turn those principles into concrete patterns for MCP and A2A. First, this is the basic pattern. Basic authentication is the authorization pattern for MCP and A2A. In the basic pattern, all workloads inside the Kubernetes cluster are implicitly trusted, and security controls are enforced only at the cluster perimeter. External clients authenticate via OIDC or OIDC and OAuth 2.1, and authorization decisions for incoming requests are delegated to a PDP. Internal service-to-service communication does not require mutual TLS or token exchange, making this pattern suitable for environments with limited exposure and non-sensitive data. Second, this is the advanced authentication and authorization pattern for MCP and A2A. In the advanced pattern, we enforce zero trust by applying mutual TLS authentication using SPIFFE SBITs between all workloads. Authorization decisions are delegated to a PDP at each workload, and token exchange must also be implemented where necessary. This pattern is recommended for environments handling sensitive data, public network exposure, or requiring strict internal security controls. Next, I'll show you a demo using Keycloak and Spire. First, let me briefly introduce Keycloak. Keycloak is an open source identity and access management solution. It provides OAuth 2.0 authorization server capabilities and single sign-on features, and is currently an incubating project under the CNCF. Keycloak's major features include support for industry standards such as OAuth 2.0, OpenID Connect 1.0, SAML v2, and more. This also covers specifications referenced by MCP, including the OAuth 2.1, OAuth 2.0 authorization server metadata, and dynamic client registration protocol. In addition, Keycloak can act as a central authorization service, or PDP, enabling policy-based access control. Next, I'll briefly introduce Spire. Spire is an open source system for workload identity management. It implements the SPIFFE standard and issues SBITs to workloads. Spire is a graduated project under the CNCF. This is today's demo architecture. We implement the advanced pattern and observe how it works in practice. First, we used CURL as a simple MCP and A2A client, and Keycloak serves as the OIDC OP and PDP. Spire acts as the SPIFFE server and SPIFFE agent. Here is a more concrete demo architecture based on the Spire quick start example. This demo architecture shows how secure agent communication is achieved by combining Keycloak, Spire, Envoy, and NGX. First, the client obtains an external access token from Keycloak and sends an MCP request to workload 1 through Envoy. Envoy checks authorization with Keycloak. If approved, the request is forwarded to the front-end NGX. Before reaching the backend, Envoy exchanges the external token for an internal token and obtained an X509 S-bit from Spire. Then establishes a mutual TLS connection to workload 2. On the backend, Envoy verifies the S-bit and again checks authorization with Keycloak. If authorized, the backend NGX processes the requested and returns the response to the client. Okay, so let's go to the demo. Just a moment. Okay. So here are all ports for demonstration. And first, these are the Keycloak ports. And this is a Spire server port. And this is a Spire agent port. And this is a front-end port. And this is a back-end port. First, I will show you front-end NGX configuration. It exposes an MCP endpoint, and that forwards requests to the backend. And it also has protected server metadata endpoint. Next, I will show you the backend NGX configuration. It also exposes the MCP endpoint, which simply returns a JSON response. Next, I will show you the source code of the Envoy external authorization filter. The key function is a check function. It first obtained the access token from the authorization header. And there are two configuration modes. One is for the inbound request, and another is for the outbound request. And this access token validator with decision mode handles inbound request. It validates the access token, for example, checking the audience claim. And then it delegates the authorization decision to Keycloak. When delegating authorization, first it added the external access token to this audience parameter, and the external access token in the authorization header. And then it gets decision result. And if the decision is true, the filter response is OK. And second, this access token exchanger mode handles outbound requests. It exchanges the external access token to an internal access token. During this exchange, it first fetches the JOTS bit and uses it for client authentication to the OIDC OP. And it specifies the external access token as the subject token parameter, and it also specifies the backend's client ID. Then it gets an internal access token. After that, it rewrites the authorization header with the internal access token and returns OK. Next, I will show you the Keycloak configuration. We use the demo realm, and we configure 2 clients. One is for front end, and we enable the token exchange feature for this client. And we set the client authentication method using the spiffy JOTS bit. Also, we define the authorization logic here. Just a moment. We set the MCP endpoint as a resource and the post method for scope. And we defined some simple user-based policy. And this policy just checks user is a whitepaper user or not. And this permission enables us to associate the resource with the policy. This permission associates MCP endpoint with the created policy. And this is the client for backend. The backend doesn't execute token exchange, so we disable the token exchange feature for this client. And we configure the client authentication method using a spiffy JOTS bit. And we configure the authorization logic as the same as the front end. This policy is as the same as the front end. Also, this permission is as the same as the front end. So let's execute the MCP authorization flow. First, we execute an MCP request without an access token. We receive 401 unauthorized response code and www.authenticate header. This header includes the protected resource server metadata endpoint. So next, we try to get the protected resource server metadata of the MCP server. The protected resource server metadata includes its authorization server information. So next, we try to get the authorization server metadata. The authorization server metadata includes, for example, a registration endpoint. This is for dynamic client registration, and an authorization endpoint and token endpoint following OAuth 2.1. So next, we try to register a client dynamically. Its token endpoint authentication method is private keyshot. And the request also includes JWKS. And this is a successful response, and it includes a client ID. So then we use this client ID to request an access token. First, we try to execute an authorization request without PXE. PXE is a mandatory standard for OAuth 2.1. When we execute this authorization request, we get an authorization error response. And it said that missing parameter code change method. Code change method is the PXE parameter. So I will explain why this check was running. And we use Keycloak client policy mechanism here. This mechanism is used to enforce multiple checks required for any profile with one setting. So we don't need to set up troublesome settings manually one by one. This time we configure the policy that invoked when an authorization request includes the MCP scope, and that multiple checks required for OAuth 2.1 are executed. And this profile includes the PXE enforcer, so the authorization request was failed. Next, we try to execute an authorization request with PXE. This time, Keycloak successfully displays a login screen, and we log in with the white Tabata user and grant access to the CUR AI agent. This time, we receive the authorization response successfully, and it contains an authorization code. And then we get an access token by using the authorization code. And then we execute the MCP request with the access token this time. Then we got a successful MCP response from the MCP server. Now let's review the logs of the Envoy external authorization filter. First, we check the inbound request for the front end. In the check method, we can see that the authorization delegation succeeded and OK decision was returned. Next, we check the outbound request for the front end. In the check method, we can see that the token exchange succeeded and an internal access token was returned. And the process completed successfully. Finally, we check the inbound request for the backend. And in the check method, we can see that the authorization delegation succeeded and an OK decision was returned. This concludes the demonstration. And as you can see, during the MCP server successfully returned the response, various IAM principles are enforced. So, thank you. This is a summary of today's session. Securing AI agent infrastructure requires robust integration of authentication and authorization. Applying CNCF IAM whitepaper principles such as OAuth for API access, Peace API architecture for authorization, and SPIFFE for workload identity enables practical cloud-native security. And today we showed how to implement them with Keycloak and Spire. That's all for today, and I appreciate your feedback via the QR code. Thank you very much for your attention. Okay, any questions? maybe that is.
First of all, thank you very much for your presentation. Quick question that I had is like agents in enterprise systems, they will need to impersonate people or person that is making the request and forward this at all the chain, and then like to acquire the permission that you need in the edge, right? The MCP tool that is trying to access a context needs to validate against the person that is trying to do that. And if it is doing that through the agent, you need to forward the token all over. If you forward the token all over, you will need to do multiple checks, right? The proposition that you did also incorporates that or not really? Sorry.
Just a moment. Maybe you refer to this kind of diagram, right?
Because in the curve that you are doing, imagine that you have a third party, right? For example, OpenAI or another hyperscaler. Once you configure the agent there, you probably will emit some kind of master key that has your token that can later on, when you do another request, emit new tokens in your name to then forward through the agent into the MCP so it can be validated at the edge where you need to access the context. Make sense?
Your question is, we may, in enterprise configuration, we may have the backend outside of the Kubernetes and some services, right? Yeah. Yeah, that is a good question, and currently only tested with this configuration, but configuring that enterprise environment, maybe that kind of problem occurred, I think. So, and in that case, currently there's no ideas, but maybe yesterday's sessions, there are some solutions for exchange its internal token to outside external services, I think. So yeah, that kind of solution can be used, I think.